Very good morning to all.
Good morning.
Very good morning, sir. How are you?
Fine.
Sir, today we have a very important topic related with light, optics.
Mm,
The subject is how we can do metrology of light,
mm,
physiological to physical. We have with us Professor H.C. Kanpal.
mm,
He's a PhD from Kumar University, Nainital, and he
mm,
has worked in National Physical Laboratory since 1983. He's
mm,
coordinated in 2014 as Chief Scientist and Head of Optical Radiation Standard Section, Quantum Phenomena and Application Division.
mm.
He achieved in the 1990 CSR Young Scientist Award. Very few scientists are from National Physical Laboratory who have achieved this Young Scientist Award. He is a fellow of National Academy of Science, Rabat. In 2021, he is a distinguished fellow of OSI. Presently, he is working as Vice President of R&D at Piam Institute Industries. Mein. Sir, basically, being having an experience of R&D and the industry, I think he is a right person
Yes.
to explain how we can use this optics or the light in the practical industries, how the industry can be benefited with his experience. Sir, yesterday I was discussing actually with him how we can help the industry taking these industries together. We are having large number of micro and the small industries. They want to develop our new products, how we can do, how the export can be increased, how the import can be reduced. All these things we can make a small group under which we can start this type of thinking. So with your kind permission, sir, I would like to request you if you kindly speak 2 words and then we will start the meeting. Please, sir.
First, I welcome Dr. Katpal uh, uh, from the National Physical Laboratory. He's having such a long experience, and I thank you also for organizing such program every Saturday. Light is very important subject. Without light, in physics is also you will find that there is some absentia, and light has given a lot of the things in the life of the human beings. The velocity of the light and all the things is related with the uh, relativity and relative theory, and without relative theory cannot compare anything in this world. At present, so many things are being sent to moon and other places, and all the things are depending upon the speed of light and all other things. So many uh, defense items are also depending upon the speed of the light and other type of things. So I welcome all of them there. I wish for the success of the seminar. Thank you all.
Thank you very much, sir. As we have with Professor Kanpal with us, I would not like to waste the time, and I'd like to request our esteemed speaker, Professor Kanpal, to kindly enlighten us with his knowledge and experience and how we can do better in the country. Thank you, sir. Please, Professor Kanpal, please, sir.
Yeah, good morning, Dikshit Saab. Good morning, Ashutosh ji, for a nice introduction. And good morning to all the participants who are listening to me on this, what is called online presentation being done from Dr. Ashutosh Agarwal ji's office. I am present with him, and I am presenting from his office at New Rajendra Nagar, where I also reside. Anyway, this has been a very fortunate moment for me that I could see him, and at the same time, I could listen Dikshit Saab on this online. So I thank you all, and I thank all the staff of Legal Metrology Department for inviting me to present whatever I know. I will
I
be
see we
talking.
have the participants from other countries also, the large number of legal metrology officers in nearby countries, Nigeria, etc.
Yeah, okay. I thank all of them for participating in this deliberation. This is basically we will be talking to each other. And in case you have got any question in between, you can also stop me in between, interrupt and ask questions. That is what I would appreciate. So I will be talking about metrology of light from physiological to physical. And why I have chosen this word, this physiological first and later on physical, that I would explain. And then I would slowly going through the slides, you will come to know how important this subject is. Unfortunately, this has been the case in the country that this subject is very scarcely taught. It is rather almost at 0 point it is taught. And when I was in intermediate class, I read few definitions of luminous flux, luminous intensity, and many times we used to forgo that 40-page chapter because it used to be only for 2 marks. So generally, students thought that why to waste such a long time for getting 2 marks. So this was almost a neglected subject throughout our career. But I did my PhD from Nainital on spectroscopy, and when I landed in National Physical Laboratory, then I was given this division optical radiation standards. Now that is called optical metrology standards or something like that. The name keeps on changing, the name is method of operation is the same. So I tell you that metrology is the measurement science, and measurement is a process assigning a number to an artifact under measurement multiplied by its unit. So when we talk of light, then light is a very small part of the electromagnetic spectrum, which makes which is either seen by human being, and it makes human to see the objects reflected from the surface of the objects, then falling on the eye, it makes people see the objects. So light is a very small part of electromagnetic spectrum, and that is generally termed as visible part of the electromagnetic spectrum because that is visible to humankind, and it extends from 380 nanometers to 780 nanometers. And rest, that optical region is a big region that starts from vacuum ultraviolet to far infrared, that we take as optical region. And out of that, this is small part is called light. So I will be talking about that small part of light which is seen by human being. And why I am talking about physiological, there are 4 physiological phenomena in the human body. Those are either seeing the object, listening, smelling, and tasting. Out of these 4 physiological phenomena, there are 2 in physics, and the rest of the 2 are not. And the 2 in physics are this photometry, what is called physiological photometry, because human being sees the part of the electromagnetic spectrum, and whatever you are seeing, you are doing the measurement. Your eye is capturing the light stimuli going to your retina from optical nerve to your brain. That is called physiological photometry, and you are doing physiological photometry, and everybody does physiological photometry every day, 24 hours, 24 into 7, except for the time you are sleeping. So physiological phenomenon. And why it came into physics, that is important, that light is a form of energy, and that energy can be measured in terms of what. Therefore, it has come into physics. Another physiological phenomena is listening. And whenever I am speaking, the wave that is coming out of my, speaking on my speaking, is striking the screen of the membrane of the ear, and it is producing a pressure on that. And because of that pressure, we keep on listening. And since pressure can be expressed in terms of numbers and with units of pressure, then this acoustics is in physics. But rest of the 2 phenomena like spelling and tasting, are not in physics because they cannot be expressed in terms of physical units. Therefore, they are not included so far in physics, but there are researches going on, especially in smelling, which looks to be a quantum phenomena rather than a classical phenomena. Therefore, this so far smelling has not been added into physics. So I'll be talking about this metrology of light, as I told you that it extends from 780 nanometer, 380 nanometers to 780 nanometers. And, I will be talking about artificial sources. We have got natural source of light, that is sun, and it gives almost all part of the electromagnetic spectrum. But I will be talking about the artificial light that is produced by human being. The first instance when man could have seen light was when he rubbed the stones, and when the stone was rubbed, the spark that came, that many of you would have experienced that when striking the stones, the spark comes that is bluish in nature. That time, this, since it can be seen by human eye, so it might be having a few number of photons in that. That's why I have given the title from few photons to few photons, that the spark might be having few photons. Now, this again, with advancement in quantum physics and all that, then again we have come to the stage that we have to measure. We will be called the most advanced persons if we can measure single photon to the extent, or rather few photons. So I have given the title from few photons to few photons. And this time when man rubbed the stones, he got the spark. This spark might have fallen into dry leaves of forest, because when a man was living in forest at the Stone Age, then the fire produced was either forest fire or dancing fire, So it is dancing fire or forest fire, which was produced as a result of that spark that might have fallen into some dry leaves, and then it extended. So that time, this artificial light, which was produced by fire, it was used by human being as a source of protection, to protect himself from the wild animals, the carnivorous things, So he used that light source, for forest fire or dancing fire, for as a source of light, as well as whatever little he could have seen that time. And at the same time, this fire was used for protection. And now when slowly and slowly advancement took place, I will go through the history of light bulb, how this was invented, and then we will come to the measurement science. So 1 million years ago, fire was used as a light source for protection. About 40,000 years ago, oil lamps were used, and most of us, to a great extent, and still being used in many countries, as well as in this country also, oil lamps are used for lighting the houses, and also in remote area of the country, these oil lamps are still used. 4,000 years ago, candles were made from fat and wax, and I have shown the picture of candle, which was perhaps made of fat and wax, but advancement has taken place, and then the things have changed, 1800, at 1800, year 1800, gas lights were first installed in London. And when I was studying in 7th class, then one of the chapters of this thing, in our English textbook, was on this gas light that was installed in London, and people used to wait in the evening for the gas to be given to the houses, and then they used to light their house by means of these gas lights that were installed. That was the story I read, and when I was in 7th class, something like 52 years, more than 50 years back, So this is the case Now, in 18,001, Louis J. Thenard observed that light is produced when metal glows, when it is heated, then the glowing of metal produces light. 1820, these are the various chronology of the developments that have taken place. In 1820, Arthur D. Rive observed a piece of platinum wire glowing in vacuum. So that must be the first step towards making the incandescent lamps in the form of tungsten lamp, which we still, love to have in our houses because of many properties of that light. But since it is a not very efficient light as compared to LED, therefore the fate is that they are diminishing from our life, But anyway, this would have been the first step towards making the vacuum, the bulb, the tungsten light. Now, in 1854, Heinrich Goebel invents the first light bulb with charred bamboo filament. And, slowly and slowly, the developments are taking place that first the platinum wire was seen glowing in vacuum. Then the concept of filament that it should be as thin as possible, so that it has got high resistance. And when this goes, the electricity, then the filament glows. So that would have been these slow steps in that direction. And 1878, J.W. Swan invents a carbon filament lamp. And I will show you historical developments, how the standards of lamps were made and how standards of optical radiation were made at different stages of time during that development. And then in 1879, Thomas Alva Edison, he invented light bulb with bamboo filament. First of that, and the patent number is written here, 223898, and this was perhaps would have been the landmark in the direction of making light bulbs. Now in 1883, Edison and Swan, the person who discovered that, these two people established a firm in London for making these type of bulbs. And in 1883, first in Germany, the light bulb was produced. And in 1890, Carl Welsbach gets a patent for production of a light bulb from the metal of osmium, there's osmium and tungsten. Tungsten, since it is called in German Wolfram, therefore the sign W is given because of the name being Wolfram. And you would be knowing that these two words combined together, they founded the firm that is called Osram. Os is for osmium and Ram is from Wolfram. Therefore, the company made was Wolfram. So this was he was the founder father of Osram company. Then in 1905, with the tantalum, the first light bulb was produced, and in till First World War, more than 50 million pieces of this bulb, which was made of tantalum metal, that were produced, and that was the situation at the time of First World War. And in 1906, General Electrics get the patent for production of Wolfram filament, that is tungsten filament, W filament, tungsten filament, and that has been going still till today. With of course, slowly and slowly development take place regarding various changes that have to be made for long stability and long life of such lamps. So in 1910, W.D. Coolidge was able to produce cheap tungsten. So once a development is made in some direction, then the other step is always to reduce the price. And once price is reduced, that is available for the societal work, and poor people can afford that. So the direction finally takes place. That is taken that to make the products cost effective. And after that, with this development that we had got a bulk filament of tungsten material producing light, slowly and slowly people started thinking in the direction that how we can produce discharge lamps and all that. And in order to increase the life of this tungsten, because when it is heated, it evaporates, and tungsten being very brittle, it is very sensitive to the thrust. And if at the point of burning, if thrust is given, then it breaks because of being brittle. So in order to increase the life, then the glass bulbs were filled with these argon neutral gases and nitrogen. Now what we call as tungsten halogen lamps. Halogen was introduced inside that, iodine especially was introduced to increase the life of tungsten. And also later on, I will tell you that this was increased, this was done to increase the color temperature of the tungsten bulb. So the bulb is outside, the glass thing is called bulb, but as such that is called a lamp, the whole entity with bulb and filament inside. And every light which is being used for purpose, for the service purpose is called GLS. And people mistakenly call only tungsten lamp as GLS. Its name is not GLS, it is incandescent lamp. Since it is used for general lighting services, therefore its name people mistakenly take that GLS, please give me GLS. So GLS doesn't exist, that is a service. So your LED is also GLS because this is being used for general lighting service. Anyway, this was the additional, I will keep on giving you additional information in between also. So, the concept was to increase the life, and then finally, first, argon was filled, then krypton was filled in order to increase the life, and then finally the turning of the filament took place in the form of coiled coil, and that increases the total, total amount of light that would be produced by such lamps. And in 1858, xenon was filled, because to increase the life. And as I was telling you that halogen was filled, W is there, and there is a reversible reaction that takes place inside a tungsten halogen lamp. W plus I2 is equal to 2W plus I2 is equal to 2WI, and 2WI breaks into W plus I2. So this, whatever comes back, sits on the tungsten that was evaporated. And because of this, reversible reaction, the loss of tungsten is prevented inside the lamp, and it increases life of the lamp. At the same time, we can increase the color temperature of the lamp. That I will come after some time, I will tell you what color temperature is called. But what we are getting today, everywhere, the total scenario in the world has changed after this, invention of LED. And, it is pervading the market like anything. And every day new development takes place. So far, we had been talking of phosphor LEDs, where the phosphor was, hit by the photon produced inside by this PN diode. Now, the other day in a BRICS meeting, the Chinese presented that they have made light bulb, these LED lamps without phosphor. So because of the phosphor, whatever intensity of light was being killed, and the quantum efficiency was not very high because of the conversion process that was taking place inside that LED. then that they have succeeded in producing, blue, green, and red LED by means of this silicon, with silicon carbide coated over that, so that the life increases. And that was one of the lectures I heard on 12th and 13th of this month in BRICS country meeting, which I was attending as a member of our company, of our this thing, as a representative of our company. Now, these are some of the lamps, the names are in German, because, Wolfram, tungsten came from Germany, and most of the signs came from Germany at that time. So all these names will be in German. So initially, the tungsten halogen lamps or tungsten lamps look like whatever is given here. And slowly, the development took place. The first development of electric lamp, which was used for general lighting service purposes, was produced in 1879, and first commercial carbon filament lamp was discovered by Thomas Alva Edison. And when he made this lamp, then one of his important quotes was that I will make electricity so cheap that only rich will burn candles, in order to distinguish themselves from others in the market, that they are rich. Then again, they will come to the initial stage, that slightly developed stage, then Stone Age, that they will burn candles. And we generally hear that this will be a candlelight dinner and so on and so forth. And this is what Thomas Alva Edison said on when he discovered carbon filament lamp, So this is additional information I am giving you. And after that, since this lamp is called energy inefficient lamp, because of this thing, that electricity is eaten to a large amount, and the light produced is very little there. Because of that, then people started thinking of developing discharge lamps. And in 1930, first high pressure mercury discharge lamp was made. And this, inside that is mercury, and mercury, when, the alternating current is given to the electrodes, then discharge takes place of the mercury ion. Because of some panning mixture inside that, the discharge takes place. And whatever radiation comes out of, due to discharge taking place inside this lamp, and the transition taking place inside the mercury atom, the radiation that is coming out hits the phosphor, which is coated on the outer bulb of this discharge lamp, and you get the white lamp. So the same phenomena is done in sodium lamp. And in the case of sodium lamp, the problem was that since sodium has got only two prominent emission lines at 5893 and 5896 angstrom units in yellow region, and it has got two bright lines that are observed in sodium lamp. Therefore, the light looked usually yellow. And most of Delhi was electrified by means of, or lighted by means of these lamps in the initial, early 70s or late 70s, like that. But once the development took place in the form of compact fluorescent lamps, then people went for that very, very fast. And there was immediately a surge of the marketing of compact fluorescent lamps, And I was fortunate that, being the chairman of ET23 of the BIS, I, because of the intelligent people sitting there, I could help them develop many standards for compact fluorescent lamps, as a neutral person working in National Physical Laboratory. So I was one of the members in that team. So compact fluorescent lamps, and these are first commercial fluorescent lamps. And still these mercury discharge lamps are used even today, low pressure, where the atoms are in very, very low number, and these atoms on discharge, they produce line-like spectrum. And since those lines always sit at particular wavelength, having a well-defined bandwidth, then those are used to calibrate the spectrometers, spectroradiometers, and all those that you use for measurement even today. So low pressure discharge mercury lamps are still used, and there are many types of lamps, cadmium lamps, then deuterium lamps, and so on and so forth. All these discharge lamps at low pressure are used for calibrating our many spectrometers and monochromators and so on and so forth. However, when they are coated with white phosphor, then they are used for general lighting service purposes. So these are the discharge lamps which are being used for general lighting service purposes. So though the first LED was discovered in something like 1960, but first commercial white LED, which is being used today widely, came into being, in 1996. And this is the picture of that of LED, which was first commercial white LED. So these are some of the developments that have taken place when we have gone from the stage of producing light by means of a spark to producing light by means of the phenomena what is called the photo the combination of p-type material and n-type semiconductors, the holes and electrons, annihilating them, and then producing the energy in the region that produces white LED. And so far, we have been using phosphors for producing white LEDs, but recently the developments, as I told you, that they have made without phosphor, LEDs without phosphor, and that is another development that has taken place as I heard recently, one of the talks, So this is the additional information I'm giving you for those who are in the process of measuring these things, or in the process of in the business of this, then this is the news for them that soon there will be LEDs, white LEDs without phosphorus. So now, as I told you that we read about electromagnetic spectrum, which extends from radio waves to gamma rays. And here in this picture, I have shown how the waves look like, what is the size of physical size, how can we explain to persons who are not in science or something, or older people who are less involved in these type of things. How can we tell them that what is the size of visible light? Then we can explain in terms of physical terms here, so on. And as I told you that a very small part of this electromagnetic spectrum, which is called light. So light should not be used in a very loose terms. Many people say UV light. So UV is not light. It is part of the electromagnetic spectrum. It is radiation. It is UV radiation, not UV light. So visible part of the electromagnetic spectrum, since it is visible to human being, that's why we call it as visible part of the electromagnetic spectrum. And it has got 7 colors with your that you know very well. And it extends from 380 nanometers to 780 nanometers. And in terms of frequency, it is somewhere from 10 to the power 14 to 10 to the power 15 hertz, So this is the electromagnetic spectrum. And when we talk of photometry, now I come to this physiological photometry, then I will come to physical photometry. And in the beginning of this talk, I told you why it is called physiological photometry, and why was it introduced in physics, as light is a form of energy, and energy can be expressed in terms of electrical parameter, that is what. Therefore, this was introduced in physics. So now we will come to what is called physiological photometry. And this slide shows human eye, because photometry deals with whatever human being sees, the colors being seen by him at the daytime, and the light intensity basically in the evening. So the nature has made us in such a way that our eye sees everything. And since the involvement of eye is there, and physiology, the science dealing with human body is called physiology, therefore it is called physiological photometry. The light stimuli coming from the light source, strikes the human eye, and then lens brings it into the retina, which is filled with vitreous humor, and a very small part of that region is called fovea. And these one that is generated into signal, that signal is taken to brain by optical nerves, and then brain processes. So the physical photometry, in this case, the receiver is eye, and then the detector is your retina, and the wires now which you are using in computers and all that, the role is being played by optical nerves or optical fibers being used for measurement. And then finally the computer, which is much more advanced than the even quantum computers coming in very soon in this thing in our life. The processor is brain, and this processor helps us see colors. And how we see colors, that I will tell you. But physical photometry deals with measuring the light stimuli by means of human being. So depending on every human being, since the measurement will be different, therefore there was a need of sophisticated science that is called physical photometry. Now, how we see the colors and how we see the intensity, that is covered by this thing here. ये कोई यहाँ पर वो है ये. So sorry. Here, this the human eye has got 7 million cones, which are responsible for the viewing of the colors of the objects. So these are three types of cones, red, blue, and green. Primary colors of vision are red, blue, and green, and those are detected by our system, this eye, in the form of, which is present in the form of cones in our eye. Since they have got conical shape, that's why they are called cones. And these cones are responsible for viewing of colors. Despite the fact that human has got only sensitivity for three colors, red, blue, and green, RBG that is called. But the processor is so strong that man can distinguish 44 million colors. That is the beauty of human eye. So one should remember that despite the primary colors being red, blue, and green, and there are the cones sensitive for these color stimuli, man can distinguish because of the very strong processor he has, 44 million colors. On the other hand, rods, in the night, when the light intensity goes down because of artificial source, in the daytime it is natural light that is due to sun. In the night when the light intensity goes down, the other part of eye, that is called rods, those come into play. And these rods are sensitive to intensity. They are not sensitive to color. Therefore, in the night, in the dark, you cannot distinguish colors. only that you can see the intensity of light by means of the rods that are present in your in our eye. Firstly, it was found that these rods and cones are confined in the foveal region, which is here in the foveal region. And because of that, the sensitivity of human eye was defined in a different way. But later on, when this research went on, one of the prominent persons in working in this field is Dr. Mahesh Chandra Gupta. He has done a lot of work in this direction, and he was very intelligent scientist, having basic ideas. So this part of this, color vision and science, that credit goes to Dr. M.C. Gupta, Mahesh Chandra Gupta, who retired in the year 2000. And before that, Dr. Das, S.R. Das was also working in this direction. So this credit goes to these two people, whatever development has taken place in India, as far as that part is concerned. And I was fortunate to have association with these people, and I have learned a lot from these two giants in this field of photometry. So I tell you that the cones are responsible for viewing the color, and the rods are responsible for viewing the intensity of light. So these both of them are about 7 millions in number. 7 million rods and 7 million cones. That's why this is called physiological photometry. As I told you, and this is the sensitivity, spectral sensitivity of these cones, how they respond to different light stimuli having different colors. This is for blue, the Z1 written as Z bar, Y bar and X bar. These are the various sensitivities for the cones for different stimuli. So here you would be noticing that it has been written CIE 2 degrees of observer, and that time these are the solid rods, the solid lines are showing the sensitivity of these colors, these cones, when 2 degree of field of view was assigned to them, because that time it was thought that these cones are confined in the foveal region that I showed you in the previous slide. And here, later on, it was found that they are extended much beyond foveal region. So then the solid angle subtended by those cones was larger in value, 10 degrees. Then in 1964, the sensitivity was redefined, and the dotted lines. So the sensitivity of these cones at different wavelengths, blue, green, and red region. Recently this nomenclature is being changed as LMS, large, medium, and small, wavelength measurements, and the color signs will be redefined after some time, as the developments are taking place. But for the time being, we can say that these are the sensitivity of these human eye. And of course, in order to give physical concept and to express in terms of numbers, these sensitivities will be redefined in the detectors that will be used for measuring the color. Now, what I meant by 2 degrees and 10 degrees is this: when it was supposed that these rods and cones are confined in the foveal region, then the solid angle subtended by the eye, at the pupil of the eye, is 2 degrees. And that time, of course, at a distance of 7 feet, we can have, or we can have an object size of 3 inches, something like, 3 inch will be something like 7.5 centimeters or so. But when it was research showed that it is well beyond the foveal region, then the solid angle subtended was 10 degrees. This with solid lines, that dotted lines are showing 2 degree field of view, and the solid lines are showing, at 10-degree field of view at the same distance. Firstly, when we were able to see very, very clearly those at 7.5 centimeters. This goes to something like 15 inches, which is more than 30 centimeter, 35 centimeter. So depending on this thing, solid angle subtended, we can define the solid angle of how much it is being subtended at the eye. So that is the meaning of solid angle. So firstly, the sensitivities were defined in terms of 2 degrees of field of view. And later on, when the researches were conducted, then it was 10 degrees field of view. Now, once we are there, as I told you that we have got rods. These are rod-shaped receptors in the eye. Those are responsible for night vision, that I have already told you. Cone-shaped receptors are responsible for daylight and color vision. And there are 3 types of cones, as I told you, that these receptors are sensitive to red, green, and blue. So these, again, in order to remind that these are the sensitivities of these rods and cones, these cones for the different wavelength regions, red, blue, and green. And this is seen. This is the color responsibility. And now we come to how we look into the objects when we look at the objects at daytime, and how our eye functions. What is the sensitivity of our eye when objects are lighted by sun, when sunlight falls on them? And in the night, how our sensitivity changes. That is shown here. And CIE, is the International Committee International, Éclairage means International Committee on Lighting, CIE. After doing research on various human beings, a large number of about 1 million people, then they produced a graph which is called V lambda. V lambda means at different wavelength how our eye works at daytime. So that's why this is named as V lambda. And it shows our sensitivity at different wavelengths at daytime. And at daytime, our sensitivity is maximum for green color. That's why green color looks exuberant, because of our sensitivity being highest in green color, especially at wavelength 555 nanometer. And this 555 nanometer is very important for defining the SI unit candela. And why this is important, that why this wavelength was taken, that will be clear in next slide, 555 nanometer. However, in the night time, our sensitivity changes towards blue. And as you are seeing in the previous case, here in the V lambda, that the light sensitivity is very low in the blue region. Here in the night time, the light sensitivity has considerably increased at blue region. And the maximum sensitivity at that time is found at 512 nanometers. Therefore, maximum of the signal lighting or the display lighting in the yesteryears were blue in color because of eye sensitivity going towards blue region, and maximum at 512 nanometers. These are the sensitivities defined for day vision and night. So these are the sensitivity, how our eye works at different stages of illumination level. And instruments that are used for measuring light are called photometers, and those who are having this V lambda response are called photometers and used for general, and everywhere you find that the photometers are having V lambda filters, and they should have this match here. Sensitivity match should be very close to the CIE adopted international value of human vision sensitivity that is shown here. And that's why we define a number, which I will tell you later on. How close the photometer will be called the best photometer in the visible, in the measuring light above certain level of illumination will be having a very good match with V lambda response. And at the nighttime vision measurements, this V dash lambda, the detector should have the sensitivity very close to V dash lambda. And now, as the development has taken place, and with the pervading of light, LED light into market, and that being a very integral part of our life, and so much so that the people are thinking of creating this human-centric lighting, because previously people were, used to be outside their house. They were exposed to natural light, and now everybody is confined inside the room. Maximum of the IT professionals and maximum of the professionals nowadays, since they live most of their 90% time inside the house, inside the room. Therefore, there are various problems, physical problems. Because of that, with the advent of LEDs, there are certain this thing which is called human-centric lighting, and LEDs will help us develop those type of lighting in the auditorium, in the lecture halls or working places, so that they can have a feel of natural light automatically at different part of the day. As sun changes its spectrum from morning to evening, the same phenomena will be adopted, and those detectors which have to be used, they have to have these types of sensitivities. On the other hand, now, because of the developments of this eye, this in LED, three important visions are there. The first one is called photopic vision. This is V lambda vision. V lambda having spectral response V lambda, that is called photopic, means the daylight sensitive vision, that is called daylight vision. And the other one is called the nighttime vision, that is dark adapted vision. Then we have got another vision, which is called mesopic. So man has got three types of responses at different part of the day. In the daytime, it's a photopic vision having maximum sensitivity at 555 nanometer. At twilight, when sun sets, at the time of setting of the sun, the response becomes a joint of both rods and cones. Both rods and cones participate in that measurement of the light, which is of course produced by sun. And at the same time, the LEDs would be producing this type of light, and therefore mesopic vision. This is mesopic response, which will be a combination of both photopic and scotopic vision. And scotopic vision is called night sensitive vision. This one is shown, which is sensitive at 512 nanometers. And here is photopic vision, which is sensitive at 555 nanometers. So these two are important, distinct. But the third one, the mesopic vision, which is very important, this slide shows that. And as I told you, that the definition of photometry or candela is given at a certain wavelength, 555 nanometers. Why that is given? Because all these three responses of eye, they are meeting at a certain point here shown here. It is at 555 nanometer. And this is very important that the wavelength, since this definition takes care of all the three types of responses, therefore the definition given was at 555 nanometers. If somebody asked why we choose 555 nanometers as defining candela, that can be had from that from this particular slide will help you understand why that wavelength was chosen. So these are the various sensitivities for this thing, and mesopic region is in between scotopic region and photopic region. So man has got three types of sensitivities for different illumination level throughout the day and throughout the day, 24 hours, So these are the various types of responses that come into play depending on illumination level. Now, again, coming to this thing, we will be dealing with only visible part of the electromagnetic spectrum. Now we will switch over to what is called physical photometry. And these things very well that our life is heavily dependent on light sources. Whatever has been written here in this slide is that have become our integral part of light. And the first thing which comes into our life, important thing is safety. And the safety will depend on reliability of the sources. So how accurately we are measuring, how precisely we are measuring, how accurately we are measuring and precisely we are measuring the light produced by such systems, the safety will depend on that. There are various types of standards and regulations that are in force to make human life safe, depending which depends on these type of gadgets which we come across our life every day, whether it is automobiles or whether it is the light bulbs at home and this thing. So this is very important that light is seen. Light products are designed to be seen by people and to illuminate all objects to be seen. Therefore, the measurement process should have a very strong conviction for human eye response. So that V lambda response is very, very important in order to make the measurements, very accurate and safe for a human being. The photometers that have to be used should have the human eye response close to the theoretically defined human eye response defined by CIE, and those photometers will be having the response. Now we know that since we are dealing with metrology, and many of this talk, before this talk, many people have talked on this topic. Last month, Dr. Sanjay Yadav, before that, Dr. Reena Sharma, and before that, many people who are senior to me, and these two people are, of course, junior to me, but my seniors like P. Banerjee and others, whoever talked, they have given you an impression of the measurement process and various units that were adopted for measurement at different stages and different years chronologically. That chronology were defined by people. But I would like to tell you that candela was taken as a base unit, SI unit in 1954. And many times I tell that I was destined to work in photometry because my year of birth is 1954. So that year candela was added as the base unit, and in 54, that's why this year is there. So at different stages, 1890, there was meter convention, then the three important parameters, kilogram and second and time and length, those meter, kilogram and second, those were adopted as SI units in 1889, and in 1954, and these other three, ampere, Kelvin and candela, those are added as base units. And then in 1960, the unit of mole was this thing. And this in 1860, this system was named as International System of Units. And in 1871, the seventh parameter, that is mole, was added to this list. So and depending on how other parameters are expressed in terms of these 7 parameters, we have got the name derived units. Those are called SI units, as those were defined in 1960. And then these many other units which are defined in terms of these units are called derived units. And nowadays, the race is towards defining every SI unit in terms of fundamental constants, especially in terms of Planck's constant. And you might have heard many lectures on this thing. One of the lectures was given by Von Klitzing few years last year, and that was the program organized by National Physical Laboratory, and many of you would have heard him also. So this these units, since they have to be independent of the definition, have to be independent of person, place, and the conditions which are there. Therefore, the main this thing is going to express these units in terms of the fundamental constants. And this is the list of international system of units, SI system that is called, and luminous intensity is the base unit, or the SI unit is candela, and its symbol is CD. Now, this metrology has gone to this advance that this much of advancement that now we are talking of photon counting applications to the extent of single photon, and many people, the present director at NPL and his colleagues are working on measuring single photon, rather in terms of few photons, precisely telling that, but there are attempts and there are detectors which have been made to detect single photons, as are shown here in quantum imaging, quantum cryptography, quantum computing. And to the extent in biotechnology, single molecule detection will take place. Here it is the this metrology. This is classical. These are in radiometric terms. And then detector calibration and quantum standards will be there. I don't know what is the status of quantum standards at present, but when I was there, then quantum standards were being talked in a big way, but somehow that has taken a lower side this at presently. So in almost this photon counting applications are pervading. The base becomes your base measurement, that is the measurement of light. So here I will be talking about photon counting applications later on, how they are being used, and at present being used for quantum efficiency detection of the detectors. So now we come to the part of from physiological photometry to physical photometry. As I told you that light is a part of energy and it can be expressed in terms of watt. And when it is expressed in terms of watt, that is called radiometry, radiation measurement. So once measurement of radiation in absolute measurement take place, that is called radiometry. And since radiometry can be expressed in terms of SI unit or derived SI unit watt, and any parameter which was physiological in nature, light stimuli measurement is totally physiological measurement. And in case that is expressed in terms of a parameter, which can be expressed in terms of SI unit, then we have given a physical base to that physiological photometry. That's why I use the word from physiological to physical. So now we will be coming to physical measurements, and what joins, the relation with joins, it was defined by CIE again. Then in terms of radiometry, that is given by this equation. This QE lambda is the energy measurement, and V lambda, I have already told you that it is the human eye response, having sensitivity at 555 nanometer, and wavelength is chosen for defining photometry in terms of radiometric parameter. What? So this relation QV, V means vision. This is a photometric parameter being expressed in terms of energy measurement QE lambda, which is energy being weighted by the human eye response. How human eye responds to the energy which is converted which is measured in terms of radiometric parameter, and the integration takes place from 380 to 780 nanometers. This is the visible part of the electromagnetic spectrum, and V lambda is already there. And this is multiplied by one of the constants, which is called maximum luminous efficacy function, Km, and it is defined as 683 lumen per watt. And what is the meaning of this 683 lumen per watt? Means that if a light stimuli is converted into energy, and if that comes out to be 1 watt, then in terms of photometric parameters, where the luminous flux means flow of the light which is taking place from the source, and that measurement is done is called luminous flux, their parameter, and its units are lumen. Then this 683 lumen per watt means light stimuli which can be converted into electrical energy, that is equal to 1 watt. If that is converted into luminous flux, it will be 683. So that is the meaning of 683 lumen per watt. So once you have got a system which can measure energy of light stimuli in the system, and if you weight that, and if you make a system which is very close to human eye response, that is called V lambda, then you are doing this measurement in terms of energy, and when it is weighted by this Km, multiplied by this Km, it will be the photometric parameters you have defined. Now there are various photometric parameters, but here this is the basic equation which has to be kept into mind, and this how we are measuring QE. If we measure in terms of watt, then this whole parameter will be watt, and 683 lumen per watt, watt will cancel out, and it will be 683 lumen. It means that we have measured photometric parameter. So we need to have a system which does radiometry, and those are called radiometers. And once we do radiometry, then we can have the physiological photometry expressed in terms of physical photometry. Now you know that physics is based on always on point sources, point objects. So here also we should have a point source, and there are certain thumb rules, because ideally you can never get neither a point object or point source, but there are certain thumb rules how we can assume a source to be a point source. Then the radiation which comes in a certain direction, in a well-defined direction, within a cone which contains this direction. You know, this is important, that the solid angle should contain the direction where it is being defined. That is called luminous intensity. And the luminous intensity IV is equal to d phi by d omega. How much luminous flux is passing through in a certain direction within a solid angle d omega is called luminous intensity, and its units are candela. But this unit is a typical unit which is very difficult to measure. You know, in direct measurement, it can never be measured, because you have to define solid angle, you have to define direction. What is most important is to define direction. So long as you are not doing that, you know, you cannot talk about you are measuring luminous intensity. So there is the measurable parameter in the field of photometry that is called luminous intensity. And luminous intensity has got a direct relation, and it is defined as the light stimuli or light falling on this area dA of, it is the incident. Here intensity is coming from the source in a different solid angle. Here on the other hand, the luminous intensity is the light falling on certain area or per unit area. This is defined as the luminous flux incident per unit area. So this is defined as d phi by dA. And if I divide dA by R square, because dA by R square is the solid angle as written above by this green color, dA by R square and multiplied by R square. dA by R square will become d omega, and d phi by d omega will become IB, and R square being there, it is IB by R square, and that is called inverse square law. Means the light incident on a particular surface per square meter will be inversely proportional to the distance it is placed. So if it is 1 unit at 1 meter of distance, it is 1 by 4 at 2 meters, and it will be 4 times at half of the distance of half a meter. So that is the meaning of inverse square law. And a well-defined this thing that this depends on the angle where it is being incident. This inverse square law is called Lambert's law, where we take the cosine angle which the source substance from the normal of the surface, that is called Lambert's law. Then EB will become I cos theta over R square. So this is the definition of candela and a parameter which can be measured, and that is called illuminance. Luminous intensity is derived in terms of units, and units of illuminance are lux, and units of intensity are candela. So in candela and lux are related through this relation, EB is equal to I cos theta over R square. So that is the total relation we have. And now this is the system that will be used for measuring the luminous intensity of the light. Here it is a detector. It is a silicon photodiode which has got a response B lambda, as I told you that the total response of the photodetector has got its own spectral sensitivity, but when it is combined with the filter with some combination of the glasses, which will make it close to human eye, that is called a B lambda corrected silicon photodiode. And as I told you that the measurement is sensitive to the angle which the surface, normal to the surface, is making with the incident light, So that is very important here to measure. So that's why a detector should have a V lambda and cosine correction in that. So this is V lambda. If you have got this corrected photo detector, we can measure EV, as I told you, or illuminance, and with the help of the length standard being very precise to the part of 10 to the power 15, 1 part in 10 to the power 15 today, or in better sense in India, it is 1 part in 10 to the power 12 or something like that. This length can be measured to that precisely R, and we know that we have got this V lambda corrected this thing, and we can convert that into electricity. And if this light source, we measure that illuminance in terms of energy, that I will show you in a moment from now, we can define the basic SI unit candela of the light source being used. This is the basic of that. And as I was telling you in the beginning, that at different stages of development of the lamps, different standards were made. Initially, it was specified candles, and with that specified candle I have shown in the lower part of this slide, which is written as UK parliamentary candle. This was the first unit of artifact that was used for defining candela. That's why they have protected it in parliament. And there is nothing like that in India, of course. But anyway, this slide was made especially by me to show you that there was a well-defined wax, well-defined wick, and when this was lighted, then the radiation that came out, or light stimuli that came out, was one candela, and that's why it is called parliamentary candle. And at different stages of light, there were specified oil lamps, then group of carbon lamps, then black body at freezing temperature of platinum, because I do not have much time to say all these things, because this topic cannot be finished in just 2 hours talk. When I have to talk, I have to little introduce something like that. I thought that since this topic is rarely taught in schools and colleges, and many of us do not know what photometry is. Therefore, I thought that I should cover as much as I can, but at different stages of this thing development, the standard should have a short time stability, it should have a long time stability, it should have minimum uncertainty in measurement of that parameter. So at different stages of light development of these systems, these different standards came into being. And finally, after in 1905, when Planck defined first time the spectrum of black body, that was the birth of quantum physics. That time, black body became the standard of light, because the energy or the radiation that exits from the well-defined area of a black body is a function of temperature only. Other parameters are constant in that equation. If you look into that, will be coming. So since it is a function of temperature, and if temperature can be measured with minimum uncertainty, then we are defining a parameter that is being emitted by the source, that is called a radiance exitance. Exiting from a well-defined angle. That's why it's called radiance exitance. So we can define that in terms of Planck's radiation law. But later on, it was thought that since black bodies are a very costly business, and the intercomparison cannot take place, those who are working in standards and involved with measurement science, anywhere, then you know that the intercomparison is very important, and intercomparison cannot be done with such heavy systems. Again, rely on lamps. That will be becomes a later generation intercomparison. Therefore, the uncertainties will be involved, and it was thought that if we can, develop a detector which is self-calibrating, means you do not need any external source to calibrate it, then that radiometer, that is called absolute radiometer, or later on it was called electrically calibrated radiometers. And if we have got this radiometer made in the system, in the labs, then it can be used for intercomparison, calibrating silicon photodiode against this, and this will be second generation. On the other hand, it will be third generation, fourth generation intercomparison with black body. Therefore, there will be the uncertainty in measurement will propagate, and there will be larger scatter in the values of the measurement. Now, since a radiometer works at this type of radiometer, which is shown here after 1979, when the candela was redefined in 1979, then absolute radiometers came into being, and this was developed by Will Blavin at Australia, and this type of system. And since this suffers from Johnson's noise, thermal noise, and the value becomes, uncertainty becomes very large because of the noise parameters, then it was thought that let the detector be cooled to helium temperature, and that's why it is called cryogenic radiometer. So in order to minimize the thermal noise and all that, a radiometer was put in a system where the helium was cooling the radiometer at 4 Kelvin. Therefore, it is called cryogenic radiometer. You will have a glimpse of those radiometers. And in 1979, though the definition which was before 79 was quite perplexing type, and nobody could understand that, whatever way it was defined. I have not included that because that would have confused. But in 1979, when physical absolute radiometers were discovered, and they were came into the mainstream measurement systems, Then CGPM, this Committee General Poison Measure of the CIP, they redefined the base unit of luminous intensity candela at a monochromatic radiation of 514 to 10 to the power 12 hertz, and this corresponds to 555 nanometer, and it is defined as the candela is the luminous intensity in a given direction. Which is very important, is the given direction, that a source emits monochromatic radiation of frequency 540 into 10 to the power 12 hertz equal to 555 nanometer, and it has got a radiant intensity in direction at 1 by 683 lumen per watt, 683 watt per steradian. It is a solid angle, you know. In terms of radiometric parameter, we have defined the light stimuli which is being emitted at 545 nanometer. Since V lambda response is a broad response which takes care of the wavelengths from 380 to 780 nanometers, so everything has to be normalized in terms of the V lambda at 555 nanometers. So that the corresponding quantities at different wavelengths should be well defined that way. And this, as I told you, that this definition is applicable to both scotopic and mesopic quantities. The standards are there being made for the mesopic this mesopic quantities. Therefore, this thing will be defined in terms of physical terms. That is watt per steradian at 555 nanometers. This is called physical photometry. And as I told you, that first time the spectrum of the radiation that was being emitted from a source that is named as black body, it was well defined by, in terms of, it was defined by Planck, and there is a long theory and story about that. I will not go into this. And this Planck radiation law shows that the radiant excitance is directly proportional to the absolute temperature at which the black body is working. Therefore, this was the beginning of quantum physics, because he introduced the concept of quanta, which is called light photon today. And in terms of that, the black bodies which were made for certain temperatures, given temperature, they are called color temperature. Now we talk of the word color here, the color temperature T. Since now this can be defined in terms of definition, and the standard is one which can be defined in terms of the definition. So this is called primary standard. But as I told you, that intercomparison is an integral part of establishing standards at different national laboratories or throughout the country, or also at international level. So international intercomparison is very important. In the case of the light sources, it becomes very, very difficult to intercompare, because ultimately from lamp to you will have to come to the lamp level, a tungsten lamp level. That will become a third generation intercomparison. Then this source based metrology or primary standards remained confined to the elite laboratories which can afford this such high heavy cost. However, it was when 79 it was defined in terms of watt per steradian. If we can make absolute radiometer and then calibrate other detectors which are having V lambda response, the human eye response, then we can intercompare then those very easily. Then this is the method that is used in order to reduce, as I told you, the thermal noise can be reduced to a large extent, and absolute accuracy becomes 5 part in 10 to the power 5. And for that, we can have certain trap detectors which take which take care of the light being reflected by the surface of the detector because of the filters being used. And the detectors are arranged in such a way that the reflected light is trapped inside. That's why they are called trap detectors. If we can calibrate those trap detectors, and these trap detectors can be used for calibrating filter radiometers, then this is the hierarchy. This is called traceability, which takes place in terms of primary standards. So there are two schools of thoughts. One is source-based standard, and the other one is detector-based standard. And since intercomparison is very handy, and it can be done very easily, therefore the detector-based photometry is being preferred. And how that is done? This is the Planck's radiation law. Here, this radiant excitance at temperature T is defined. Here are all constants at a given wavelength. Then at a given wavelength, it becomes a function of temperature only because C1 is constant, C2 is constant here. Then these being, the parameters that are involved for this radiant excitance, then this becomes the definition of black body. And that was first given by Planck. Therefore, this is called Planck radiation law. And it is the base for making primary standard of optical radiation. And if that energy is weighted in terms of V lambda, that becomes the primary base for photometry. Now, this is one of the slides when I was in NPL, I have taken at that time. This is the black body, which was working at that time. And now my colleagues are there. They must be taking care of this type of system. Here, all parameters are defined. Its emissivity is about 999, and radiance uniformity and so on. And it works at a range of temperatures. Therefore, this is the primary standard which is existing at National Physical Laboratory. And now I will go because that I have already talked about this. Then I will talk about this absolute radiometer as primary standard because this is a self-calibrating device which was made in NPL for first time defining the standard of optical radiation. It is based on electrical substitution because the radiation which is falling on the detector like a cavity or a surface, black surface, which absorbs 99.9% of the radiation, and all these sources of errors are taken into consideration. And then whatever temperature rise takes place as a result of the absorption of radiation and reaching at steady state, then that is produced, if that's the steady state is produced by heating the detector by means of electrical heater, because we can define current and voltage parameters with greater accuracy, and they are well defined. Current can be defined to a greater accuracy with least uncertainty. At the same time, voltage in terms of voltage standard which exists at NPL, then a parameter which was physiological in nature, if could be expressed in terms of current and voltage that finally multiplied together make watt, then we can define this radiometer. We can make a radiometer. We are doing radiometry. And finally, we are defining the light stimuli in terms of electrical watt, and that is a physical parameter. So this is the principle of electrical substitution radiometer. And this was the first radiometer made in NPL. Here is a radiometer. I have already told you that it is electrical substitution radiometer. The V lambda filter is made because we have to make the visible part of the electromagnetic spectrum. We have to measure, and this is the lamp which is emitting visible spectrum, infrared, and so on. So taking into consideration that infrared doesn't go inside and only the visible part of the electromagnetic goes, this V lambda filter is this, and there are many considerations why these are looking tilted. So taking into consideration, we could deposit gold black coating, and gold black has got property that lamp black while absorbs 95% of the radiation, gold black absorbs 99%. And in order to increase the efficiency of this absorption, a mirror was put over here, gold coated mirror, which reflected another 1% reflected from the surface of the radiometer, again back to the radiometer. Then the absorption could be measured up to, the absorption increased up to 999. This graph here shows the steady state that reaches as a result of radiant heating and as a result of electrical heating. Because you can never get a stable this thing. There will be slow rise in heating temperatures. Therefore, you have to take into consideration that error into measurement due to this property. But a balance is obtained that whatever thermo EMF is produced by measuring it means of thermopile, if the same thermo EMF could be produced by electrical heating, balancing current and voltage, then we have expressed by means of this radiation, we have done measurement of this parameter EE lambda. This here, EE lambda below there, because it is making me difficult to go into this. So EB is equal to Km into EE lambda we have done with the help of radiometer. Since this radiometer has been, combined with V lambda, so we have this total parameter E lambda, V lambda measured by means of this radiometer, E lambda, V lambda, D lambda, in the range of the V lambda parameter, that is 380 to 780 nanometers. When we multiply it by Km, we are measuring the illuminance produced by the lamp at a well-defined aperture, which is written as A here. This is the limiting aperture. Then measuring this distance precisely by means of length standard and all that, you can have the parameter EE lambda and R. When you have done EE lambda measurement and R measurement, multiply those two, E equal to R square will be equal to I. So we can establish a luminous intensity standard by means of this. So this is the detector-based radiometry, and I have already told you about the intricacies. Those are involved in measurement of source-based radiometry. And this is the facility that time when I was there. Then it was upcoming facility. I'm grateful to this thing that is still being used. My colleagues must be doing in this with this cryogenic radiometer and other things into consideration. And this is the picture of radiometer. This is based on the same principle which I told you about room temperature radiometer. Only the difference is that in order to reduce the thermal noise so that the uncertainty in measurement goes high, this system is used. And when such a low temperature is being used, all seals and all things they have to be taken care of. Therefore, the system looks a bit complex and complicated, but at the same time, it looks beautiful also, So this is the inside view of the radiometer. Now, I will go as Dr. Ashutosh Agarwal told in the beginning that we would be dealing with how we measure these things, the photometric parameters, because of for the benefit of industry. I will take about 10 minutes on this thing, and as I feel slightly exhausted, then we will break for 5 minutes. So after 5 minutes, we meet here at this point.
Thank you, sir. Thank you. We can break for just for 5 minutes and we'll be back within 5 minutes. Thank you.
Okay, na?
Yes.
Welcome back. Since there is constraint of time, therefore I thought that let us go for a 2 minutes break. Now, as I told you that measurement is a process, and you have been told by all these things earlier by earlier speakers also. So it depends on what we measure and how we measure it. There are several techniques, so we call that as how we measure, and there are several parameters and several types of measurements that is called what we measure. So as I told you that in so I told you that I will just introduce you the techniques that are used in photometry and what are the parameters involved in that. That is called types, techniques, photometry and colorimetry. We measure the total flux, the light total integrated coming from a source. Angular intensity, as I told you that intensity is a directional parameter. How we measure that at a surface that we have defined as E, illuminance, and we do spectroradiometry. If we split that light stimuli into different colors, then at the source, if you split, then that is called spectroradiometry. So these are the techniques and types, and depending on techniques and types, there will be various names to them. They are given different names. Photometry of this total flux is called total luminous flux. Its units are lumen. Radiometry of total flux is total radiant flux. This is units watt. Then lumens and watts are connected to each other through that relation. EB is equal to km into watt, and watt cancels out that. So the photometric parameter lumens can be expressed in terms of watt. And when we are dealing with one of the spectral components in the range from 380 to 780 nanometers, it will be watts per nanometer. So we can define that spectroradiometry. Nowadays, spectroradiometry makes the base for all these measurements, you see. And angular intensity, this word has been introduced already. The same picture is here. And it is radiant intensity would be in watts per steradian. And angular intensity in terms of visible light will be lumen per steradian. Those are connected through km. Then lumen per steradian will be expressed in terms of watt per steradian. And similarly here, it will be watt per steradian per nanometer as far as this spectral component is concerned. Then on the surface, it is called a lumen per meter square, how much light is falling, luminous flux is falling per meter square, and how much energy is falling is watts per meter square, spectral component watts per meter square nanometer. Now, luminance, and this in literary terms called brightness, and this is a parameter which human eye sees directly. It says the brightness of this source is better. We make a statement like this, that this source is looking brighter than the other source. It means that human eye can measure directly the parameter luminance. It is only human eye in nature which can measure luminance directly without this thing. So this parameter luminance is the property of the source, and it is defined as candelas per meter square or lumen per steradian per meter square. So candela is lumen per steradian. That's why it is lumen per steradian per meter square. And its radiometric counterpart will be radiance. Therefore, a parameter luminance will be from the surface area, from a particular area of the surface, how much radiation, luminous flux is coming is called luminance. On the other hand, if it is from a point source, this will be candela. So radiance is the radiometric counterpart of luminance, and spectral component, of course, as defined by me earlier. Now, how to measure luminous flux? As I told you that the integrated light that is coming from a source is called luminous flux. And luminous flux can be measured by means of a sphere called integrating sphere. Why it is called integrating? Because it is integrating the whole light which is coming out of the source and finally making it incident on the detector P, which has been shown by green light here, green color here, because V lambda, it should have a V lambda response. And in between, you are seeing a screen which is called baffle. Since it baffles the light from directly falling on the surface, therefore it is named as baffle also. So since this light from source should not directly fall on the detector, therefore it is called baffle. It baffles actually. So the parameters where it has to be placed, and depending on size of the source and this thing, source and the size of the integrating sphere, we can have the luminous flux measured, and outside this there is a auxiliary lamp, because the standards being produced by National Physical Laboratory would be having, because those are very costly affair, and those are protected like anything. Therefore, the sources which you have are of different sizes and shapes, So they give you a standard of particular shape and size, having a defined color temperature of, generally it is taken as 2856 Kelvin. That we can discuss anytime later, but here it is important in order to determine the absorption of the light takes place inside an integrating sphere because of the paraphernalia we have put inside the detector. There is a baffle, there is a source, there will be hanging system, there will be other things, and any perturbation, anything inside the integrating sphere is a perturbation on the measurement of light. Therefore, in order to assess how much energy is being eaten by the source whose luminous flux has to be measured in terms of the standard that has been provided by NPL, here is a source that is called auxiliary source. And that auxiliary source helps in measuring the absorption and that ratio of the signal that comes from as a result of putting the standard, and then the lamp is has to be multiplied by the electrical signal that will be produced as a result of the radiation emitted by the source. So a luminous flux in a process called substitution method. Substitution word is used because here the light source which is being measured substitutes the standard. That's why the word substitution method is used here for integrating sphere. On the other hand, a goniometer is called the primary standard of luminous flux because here the detector is made revolve around the source in all 4 pi direction by means of this picture shown here. That detector is moving in different angles at 2 pi, and then it is completing the whole sphere, that is imaginary sphere being formed as a result of the movement of this detector. That's why we can measure luminous flux in absolute terms. So once this standard is made by NPL by measuring the very good equipment they have got from, they have procured now, this standard will be used for making the life easier and fast by means of by using integrating sphere, and you can have intercomparison. Intercomparing the standard with the light source being measured. That's why that is called substitution method. It is, on the other hand, absolute measurement of the light flux that is being emitted by the source. Now, this system is used for measuring the color temperature. I do not have much time to tell all that, but this type of system is used for assessing by NPL that the detector submitted by you has been, has the well-defined V lambda corrected silicon photodiode or not. So this helps determining whether the detector is having V lambda response or not. If it is not, then you are not doing luminous flux measurement, because maximum of the light will be having all other components like UV and infrared in many cases. Therefore, the measurements will be erroneous. So they have a system where they can assess your value by means of this type of system used. So this is used for measuring the color temperature and also the correction for checking the B lambda correction. So, and now I told you luminance also we can measure. Luminance can be measured in terms of standard luminous flux F as shown by this formula. In this case, you see that all the rest of the parameters for a given system like this, where a sphere is having a well-defined R now, and the surface which has been coated with a white surface, that could be BaSO4 or spectralon, the reflectance is well defined. So this parameter L is just dependent on this luminous flux, and in case you have got luminous flux source calibrated by NPL as a standard, then you can establish a luminance standard by using integrating sphere. At the same time, you can use by means of a luminance meter by using a Lambertian diffuser and illuminating that with the help of a luminous intensity standard. We know that illuminance has been produced on the surface, and so this is this system luminance meter is used to this system is used to calibrate luminance meters which are in terms of the defined parameter, illuminance, luminance, the intensity in terms of illuminance, and illuminance multiplied by the reflection of the surface in 2 pi direction, then this luminance meter can be calibrated. So this is another attachment for luminance calibration. And here is the cosine correction. What is the meaning of cosine correction? That cos 0 is equal to 1. At cos 90, there should be no radiation falling on this thing. If you take the source from 0, which is just parallel to parallel to the normal of the surface of the detector, then it should read maximum value, that is cos 0. And when the source is brought at 90 degree to the detector, then the signal should be 0. That is the meaning of cosine correction. Now, as I told you that color measurement is also based on the visual perception. And we have already talked about the responses of cones for different wavelengths, that is for red, blue, and green. The color science is based on the physical picture. Whatever color is seen by human eye will be visual, physiological physiological colorimetry. But when we define, when we have well-defined detectors which are having responses as the photometer having defined response V lambda, then we can have the color measurements done. Here, for example, a source can be defined in terms of physical terms as energy radiated by it at different wavelengths. That's why it is called spectrum. And we can define the reflectance, that is the light reflected by any object which is seen by human eye. Then that in terms of spectral measurements, it can be defined here in the wavelength range from 380 to 780 nanometers. The total influence of the spectrum of the source, artificial source, to that of the reflectance of the surface which is being seen is this, this one, which is equal to this visual this thing. So the total influence of one on other is this. Now, if this is weighted by the red response, green response, and the blue response of human eye, then we can have the measurement done in terms of numbers. And when we do measurement in terms of numbers, then we can define what is called colorimetry. So these are three stimuli, X, Y, and Z. So we can have these values X and Y and Z values measured by means of a tri-stimulus colorimeter. It is named as tri-stimulus because our three stimuli we are measuring, which our cone measures, actually. So the influence of the source spectrum by the reflectance of the surface, and then falling finally on the cones, which are having these responses, and detectors, physical detectors, which have been made as per the response of the cones at different wavelengths, we can have these numbers. And these numbers can be used for defining, which is called color coordinates. And the X coordinate will be capital X, that light stimuli for red, upon X plus Y plus Z, what the three stimuli are measuring or the detectors are measuring. And then Y coordinate will be small y will be equal to capital Y upon capital X plus capital Y plus Z. And since X plus Y plus Z is equal to 1, therefore the third parameter is not, there is no need for measuring this, that automatically comes. Therefore, you will see that the colorimetry chart is two-dimensional in nature, X, Y, and this thing. The tongue diagram is used for representing the color coordinates and the color property of a source. And the colorimeter that is used for measuring the color is called tri-stimulus colorimeter. And now this, when we have got these numbers, we can define, we can have the physical measurement of the color of any object. It can be in reflection mode. It can be in the transmission mode. When the source, when the color of the source is being directly measured, then it will be air in between, and everything is transmitted by the air. Therefore, we will not have something like this picture. The source will be directly measured by this tri-stimulus colorimeter, and it will give us the value in terms of these numbers. And when these numbers are divided, as I told you, then we can get the XY coordinates of any source or any specimen or any object that is around us, So we can have everything defined in terms of color, whatever is seen by human being. Now, as the time is not there, so let me end here, because it will take another 1.5 hours to go for photon counting schemes and all that. And I thank everybody for being patiently listening to me. And I hope that I had been able to convey whatever I have learned so far, whatever little I have learned so far in this big branch of science, which I know perhaps a little low percentage of that subject, I can say 0.01% or less than that. Then still after that, knowing such a little amount of this vast subject, I would have been able to convey you how the measurements are done, what are the fundamental things involved in such measurement, and so on. So I thank you all for having patiently listened to me and for your presence here today. Thank you.
Thank you very much, sir. Actually, your presentation was very good, and certainly we try to understand a lot. I think that all the participants have tried to understand. I would like to request all the participants to kindly switch on their video and switch on their mics. We are just making you, all of you, the participants, the panelists, so that if you want to ask anything, you can ask, number one. And sir, this is a vast topic, I understand. I would like to request you to have another session on the similar topic, or in continuation of that, how to do the calibration, how to calculate the uncertainty, and if you kindly share with us the uncertainty sheets or the Excel sheets with which we can share it with the participant, large number of participants who can use these Excel sheets to calculate the uncertainty in their practicals. It will be a very good exercise. I would also like to request you to kindly allow us to share your presentation, whatsoever you have done today, to all the participants, and the video which we have recorded today, we will also place it in our channels so that the participants can be benefited in future whenever they need or they just have a confusion to understand something. This is one thing, sir. Secondly, suppose you kindly make all the participants, the panelists, so that we can take the pictures and we can continue that. Secondly, the most important thing which I feel is the trust. We should have the trust on each other. We should have a trust on the science, on the scientists, on the system, that what we are understanding or what we are doing is correct. Unfortunately, in many ways, what I observe that there is a lack of trust on each other. We don't trust each other. So that type of thing, when we are going to the market, we don't have the trust that it is correct. When we are doing some transactions, we don't have the trust. So I hope that first of all, we should start having trust on ourselves and then on the nearby or our near one or the dear one to whom we used to do the transactions, daily transactions. All the participants from India and outside the country, I would like to thank all of you. Santoshi, have you taken the picture?
Taking sir, but video is not switch on.
Okay, no problem. I would like to again request all the participants to quietly switch on their video so that we can take the pictures for uploading it on our all websites, on our all portals, social media portals.
There are many aids here.
Yes, sir.
It's a very, good to see that there are many aids here.
Yes, sir.
And if there are questions, I would be glad to answer that to the extent, I would answer all those, I will try to answer all those questions to the best extent possible. And the knowledge I'm
Please,
having
if
or
anybody wants
gained.
to ask anything, sir is here. Professor Kanpal, actually, I would like to tell you that he is having more than 40 years of experience because he has already completed, retired 10 years back, 30 years in NPL, and then again attached with the industry, doing a lot of research work, doing a lot of development, establishment of the new technology. So it's a very good exercise. If you want to ask anything about the photometry, about the light, you can ask, please. In India, this motivator and a big design we have.
Answer.
Thank you. Thank you very much. Thank you to all. We will